Hi students, I'm Dr. B. Ravi Kumar, Associate Professor, Department of SCE, Institute of Aeronautical Engineering. Now, this class, I'm going to explain some problems related to synchronous, like synchronous counter or synchronous sequential circuits. We know that to design a synchronous sequential circuits, we must have followed some steps. Those steps are, the first step is the problem specification given by state diagram. The state diagram clearly says that, okay, what is the final specification of the particular circuit diagram need to be designed. Once we know the state diagram, we create that state table. That state table having present state with the representation of each state with represented by a letter, English letters, and then next state, some kind of state tables having like input combinations, like input is x is equal to 0, what is the next state, and x is equal to 1, what is the next state. By considering inputs also we can create that next state, and then output. Okay, then if it is at all any requirements for the state reduction, some states have any redundancy in the particular entire columns, then we have to reduce those states using the state reduction. Then assign the binary values to each state. Basically, we have assigned some English letters to each state in the state table to replace that letters into binary representation of each state, and then determine the number of flip-flops. So based on the states, okay, how many number of flip-flops are required. If there are 4 states, so we require 2 flip-flops are enough to create that 4 states. So likewise, we are determining the number of flip-flops. And the next step, choose the type of flip-flop to be used. So as I earlier told you that, okay, what type of flip-flops are required. So if they are not specific, then you have to choose that one, any general specific like JK flip-flop. If it is counter, it is counter, then we prefer that toggle flip-flop. Or if you want to counting using the shift register, then we prefer that D flip-flops to transfer the data, simply that input to pass to the output. So likewise we can prefer that flip-flop to be used. Then from the state table, then derive the circuit excitation table and output table. In this excitation table, so we can create that, okay, for the flip-flop input and output. Okay, what are the what are the columns need to be placed in that output column with the help of excitation table. Then once we create that excitation table from the state table, then we can easily identify or simplify the Boolean function of each column in the flip-flop input and output with the help of mapping or like map, whether it is K-map or any other method, simplified method. Once you derive the simplification of simplified Boolean functions of each flip-flop input, then we draw the logic diagram. Let us see that on one more example by considering all those steps. So the problem taken from the question bank: construct a 4-bit binary counter using D flip-flops, which counts all possible odd numbers only. So in this, the specification has given 4-bit binary counter which counts all possible odd numbers only. If you take 4-bit, nothing but 0 to 15. So whenever the circuit initiated by some 0, then it starts to counting only odd numbers. 1 is the present state, the next state is 3. If the 3 is the present state, next state is 5. So that we can, it will generate only odd numbers at each time or each state. If you see this diagram, for example, this state diagram, whatever the specification has given represented by some state diagram, for example. So initially the circuit is in 0 state, then it will move to state 1, 3, 5, 7, 9, 11, 13, 15. So we can represent it with that one. So initially it is in 0 state, the circuit. Then it will move to, for the application of the clock, it moves to the first odd number 1. And when again application of the clock, it will move to the state 3. It will move to the state 5. Then it will move to the state 7. Then it will move to state 9. Not step, the number, like odd number 9. It moves to the number 11. It counts number 13. Then it counts number 15. Then if our wish, then it can keep on repeat after 15. It will again go back to that one number, odd number 1. Again it will repeat 1, 3, 5, 7, 9, like that. So this is the state diagram. In this state diagram, for this state diagram, we can create a state table. So using the D flip-flop, okay. So next we will see that state table. What is the state table? A state table having present state. In that present state is possibly, actually it has 4-bit number. So it requires represented by this state, each state with 4 letters. A, B, C, D. The next state represented by, we can take same A, B, C, or A, N, B, N, C, N, D, N. Let us take, initially it is in 0. Initially it is in 0 state. We will take pointer, color. If it is 0, 0, the next state is first odd number is 0, 0, 0, 1. If present state is 0, 0, 0, 1, the next odd number is 0, 0, 1, 1, nothing but 3. If present state is 0, 0, 1, 1, the next state is nothing but next odd number is 0, 1, 1. If present state is 0, 1, 1, the next state is 0, 1, 1, 1, 7. If present state is 0, 1, 1, 1, 1, next state is 1, 0, 0, 1. The next state is 1, 0, 0, 1. So the next odd number is 11, 1, 0, 1, 1, 1, 0, 1, 1. The next number is 13, 1, 1, 0, 1. If present state is 1, 1, 0, 1, next state is 1, 1, like 4 ones, 15. The present state is 15. The next state is, according to state diagram, it will goes to 1. Again it will repeat to the odd number 1. So what if the number other than this, if the present state, for example, it is a 4 variable, if we are assigning A, B, C, D with 4 numbers, Like, then what about if the present state is other than odd numbers? If the present state other than odd number, for example, present state, next state, if the present state is 0 0 1 0, 0 0 1 0, the next state is like AN, BN, CN, DN. Next state is don't care. So we are not care about this one. For 2, for 4, we will treat it as don't care. For 6, for 8, for 10, for 12, for 14. For all, it will be treated as don't care. Don't care. So with the help of this state table, we can create the excitation table. So in this case, so not required to reduce any state table. So reduction in the state table not required. So we'll go to excitation table. In this excitation table, we create the present state, next state, and D inputs, D flip flop inputs. We have to design the circuit diagram with the help of D flip flop. So D inputs. We will call it as names A, B, C, D. But in binary form, we can take the 0, 0, 0 to 4 ones. In this, each column, we create one flip flop. So it requires 4 flip flop. Number of flip flops are required is 4. So identify the number of flip flops for D1, D2, D3, D4. These 4 flip flops we can take D1, D2. So as we have created the state table, according to state table, initially it is in 0. Then once apply the clock pulse, it will move to first odd number 0, 0, 0, 1, 0, 0, 0, 1. Then it will move to 0, 0, 1, 1. Then 0, 0, 1, 1, 0, 1, not 1, 0, 1, not 1 is the present state. Next number is 0, 111, 0, 111. Then we have 9, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1. Next present state is 11. Next is 12. Sorry, 13. If the present state is 13, the next state is 15. If the present state is 15, again it goes to 1. What if for like even numbers? Okay, so this is initially 0, this value is 1, this value is 3, this value is 5, this value is 7, 9, in decimal form 11, 13, 15, again go back to 1. So for example, any state, the circuit diagram which is in state 2, I am just representing in a decimal form. State 2, state 4, present state the number is 4, counting the number is 4, 6, 8, 10, 12, 14, the entire values. If we consider, if we are not considering, then we can't take that, they don't care in the minimization function. So if you consider this even number, for example, unfortunately the first the state is in even number, then the next state, like it won't goes, it won't consider and it won't care. Otherwise we can just remove this all the other states. So by creating that k map, we can consider the don't cares. Next, once we finding the excitation table, then creating the present state, next state, with the help of excitation table we fulfill the data inputs, D flip-flop inputs. One simple logic for the data inputs, D flip-flop input is basically in the excitation table, whatever the present state, for example Q is the present state and Qn is the next state, and what is the excitation table D input. If present state is 0, next state 0, present state 0, next state 1, present state 1, next state 0, present state 1, next state 1. In this case, this just copy this next state, because whatever the D input just copied the D flip-flop output. So 0, 1, 0, 1. Similarly, by following this table, we can create the D1 column, D2 column, D3, D4. We just copied this one. We just copy this one in the D flip-flop only, D flip-flop based design. So this is 1, 0, 0, 0, 1. Next 0, 0, 1, 1, 0, 101, 0, 111, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 4 ones, 0, 0, 0, 1. Next, don't cares. All 4 don't cares, remember. All don't cares. So, we can now create the mapping minimized Boolean function for D1 each column. What is the required combination circuit connected to the D flip-flop input? D1 D flip-flop input, D2 D3 input, D4 input. In order to get that combination circuit, we have to finding with the help of mapping, K-map. So with the help of K-map, we find out the D1. So in this, in order to get the D1 input, so we can take the present state inputs are, and is there any possible inputs, we can consider inputs. But in this case, no inputs, we can take only A, B, C, D inputs. So A, B in the present state, A, B, C, D is the CD are the inputs. With the help of K-map 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So like that we can create for both D1, D2. For D2, A, B, C, D. If the present state this one, what will be the next state we will get? Zero, 1, 1, 1, 1, 0, 0 0 0 1 1 1 1 0. Likewise we can create for D2 D3 D3 ABCD 0 0 0 1 1 1 1 0. Likewise we can create 4 K-maps for 4 D data inputs, D flip-flop inputs. 0 1 1 1 1 0 1 1 1 0. In this case, now we will create that okay. So if you take this one, first 4 zeros and then 4 ones, 0 and then don't cares. So let us see that first 4 zeros 1 3 5 7 1 3 5 7 are the zeros. 1 3 5 7. This is 0 1 3 4 5 7. You can take that column, sorry, this one, zero 1 3 5 0 1 3 0 1 3 5 zeros, and this 0 is 15, this is 12 13 15 14, and by seeing this don't get all the even numbers. How can we get all the even numbers? By substituting this one. So this is 7, who are the get ones, putting like make 1 in that square box. 7 9 11 13, 7 9 11 13, 7 9 4 5 7 6 8 9, this one is 9 11 13, 7 9 11 13, 8 9 11 13, there is 13 12 13 15 14, 7 9, like 7 9 7 9 8 9, this one is the 9. Now remaining all are don't gets, because if you check with this one, it is a 2, it is a 4, it is 6, it is 12 12 13 15 14 14 8 8 9 11 10. So by substituting this one for the D1 column, we can make this like squares and quads group together to get the minterms, prime implicant. So there are 4 ones. In order to cover those 4 ones, the maximum possibilities of the quad is this one. So then another quad is this one, and there are only one left. To create that one, there is no possibility, only possibility is pair. Next we will see that second column. We will see that second column by substituting 0 0, all the possibilities I am directly writing. x1 0x, x1 0x, x0 1x. We can create, this is a quad, we can create this quad. And the third one from the table, we can write down like this 0. These are the actually for every table, these are the duplicates. You can create this one. Then in this case, these are ones, these are zeros. In this case, these are ones. Okay, so here to cover all ones, we take this quad only, vertical quad. To create all ones, this is one quad and this is another quad. So to finding this one, so for this quad, the row wise, what is the common letter is 1110, the common is 1, A. And vertically, if you take this one, what is the common with the first two columns? C bar, A C bar. For this one, for this quad, we will take A B bar. For this quad, this pair, we will get three letters A bar B C. Similarly, for D2, you will get a B C bar because it is a common one is row wise. For this one, row wise common is B 0111 low. B is common, and vertically C bar plus another quad. For this quad, B bar C. This also can be represented by B XOR C. And D3 is equal to, you will get only vertically, horizontally cancel together vertical C bar D. And D4 is equal to CD plus A bar B bar. Now take those four expressions and draw the logic diagram. So if you take these four D flip-flops, D input Q bar, D1, D2, D3, D4, Q bar, Q bar, Q bar. So this is like the next state. The present state is the states here we can represent it by A, B, C, D, like this. So in order to create the combination circuit, so what is the expression for A? D1 is D1 input AC bar. It is a C bar. If it is C, it is C bar. AC bar, AB bar, and A bar BC, A bar BC. These are connected with the OR gate. This is output is connected to D input. This is D1. Next D2 is equal to B XOR C. You know that B here it is. This is B. This is C. Exclusive OR. You can connect exclusive OR. This D2 connected back to D2. We can take the path in the D2. D2 is this one path. Next D3, C bar D. This is C bar. This is D. Connected with 1 and get. Take back to the D3 input. And finally D4 is equal CD, A bar, B bar. This is C. This is D. A bar, B bar. A bar, B bar. This is get back to D4. And we have a common clock. So each flip-flop initiated by connected to common clock. Clock pulse. So that we will get that this is a flip-flop part. That's this 4 flip-flops, and this is combinational. These are the all this one combinational connections, and it will connected back to flip-flop input. So that finally we will get the logic diagram. This is the way to design sequential circuits, synchronous sequential circuit. These are the references. From this reference, like IARE question bank and digital design by Maurice Mano. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.